Ancient astronomers etched celestial secrets onto clay. This knowledge would one day help Isaac Newton unlock the universe. We are tracing the incredible manuscript trail from Babylonian stargazers to the birth of modern physics. By the end, you will see how a chain of scholars preserved this wisdom across 3,000 years. How did observations made for ancient kings end up on the desk of a genius in England? What does this tell us about the very nature of discovery? This story reveals that science is a conversation spanning centuries. What forgotten connection between past and present most surprises you? Clay tablets from Mesopotamia hold the first equations of the sky. In the Fertile Crescent between the Tigris and Euphrates rivers, a priestly class of astronomers looked upward not for poetry, but for prophecy. They believed the gods wrote their intentions in the stars and planets, and so they meticulously recorded every celestial event, from the slow march of Jupiter to the sudden vanishing of the moon during an eclipse. This was not a hobby, it was a state-sponsored science, a vital tool for advising kings and guiding empires. To make sense of the heavens, these anonymous scholars invented a powerful new language, the language of mathematics. They gave us the base 60 or sexagesimal system. We still live with their innovation every time we check a clock with its 60 seconds and 60 minutes, or measure an angle with its 360 degrees. This mathematical toolkit allowed them to do something truly revolutionary. They began to predict the future. By observing patterns over centuries, they could forecast lunar eclipses and the complex loops of planets with a precision that would not be matched for over 1,000 years. All of this knowledge, these celestial computations and star catalogues, was carefully impressed with a stylus onto damp clay tablets, creating the distinctive wedge-shaped script known as cuneiform. These fragile libraries of baked earth became the bedrock of all Western astronomy, a foundation so solid that its echoes would eventually reach a desk in Cambridge. But how could such ancient and fragile records possibly survive the collapse of empires, the rise of new religions, and the long, dark centuries to come? The fate of this knowledge now hinged on a great and unexpected transfer of power. The silent, dusty halls of the Library of Ashurbanipal held the world's memory. In the 7th century before the Common Era, this Assyrian king was not just a conqueror of lands but a collector of knowledge, amassing in his capital city of Nineveh a vast repository of tens of thousands of clay tablets. This was not merely a storehouse, it was the internet server of the ancient world, a central archive where the scattered astronomical observations from across Babylonia were gathered, copied, and systematically organized. Scribes worked diligently, standardizing the celestial diaries and omens that had been recorded for generations. Without this obsessive, centralized effort, the fragile clay records of early astronomy could have easily crumbled into forgotten dust, their mathematical insights lost to the endless cycles of war and decay. The library's holdings were breathtakingly precise, containing detailed accounts of planetary positions, lunar cycles, and eclipses, all meticulously notated in cuneiform. The eventual destruction of this great library was a cultural catastrophe of unimaginable scale, a fire that baked the very tablets meant to preserve knowledge, seemingly sealing their fate forever. Yet, in a cruel twist of irony, that same fire is what hardened and preserved a fraction of the collection for archaeologists to unearth millennia later. These surviving fragments, these scattered pieces of a broken whole, tell a story of resilience. They prove that the knowledge itself was tougher than the empires that fostered it. The trail of these celestial secrets was now faint, but it was not broken. Who would find these scattered pieces and dare to pick them up? The fire that consumed Nineveh did not extinguish the knowledge it held. Centuries later, that same Babylonian data found a new home in the most famous library the world has ever known. Alexandria, a city built at the crossroads of continents, became a crucible where East met West. Here, Greek thinkers who loved geometry and philosophy encountered the vast observational records of the Babylonians. They saw the raw power in those numbers, a centuries-long diary of the sky that their own young tradition simply could not match. A brilliant astronomer named Hipparchus was one of the first to grasp the potential. He got his hands on Babylonian eclipse records stretching back generations, and he realized something profound. Their data was the key. He could use their precise timings to uncover a slow wobble in the Earth's rotation, a cycle we now call precession. This was not just borrowing, it was a fundamental collaboration across time. The Greeks provided the elegant geometrical models to explain the cosmos, while the Babylonians supplied the hard numbers to make those models accurate. This fusion of two great scientific cultures reached its peak with Claudius Ptolemy. His monumental work, the Almagest, became the astronomical Bible for over 1,000 years. And at its heart, beating with a steady, ancient rhythm, was Babylonian mathematics. Ptolemy openly used their parameters for the motions of the moon and planets. He adopted their base 60 system for his calculations. His entire cosmic scheme, with its complex circles upon circles, relied on the observational bedrock laid down by scribes working 1,000 years before him. The celestial knowledge, once pressed into clay for Assyrian kings, was now meticulously copied onto papyrus scrolls in Greek. It had been translated, refined, and embedded within a powerful new theoretical framework. This was the great synthesis, a hybrid science born in the vibrant intellectual haze of Alexandria. The trail of the manuscript had not just survived, it had evolved, becoming richer and more potent. But the Library of Alexandria, too, would eventually fade into history. So how would this newly forged Greco-Babylonian science survive the next great collapse? Its survival now depended on a new group of scholars who would emerge from an unexpected quarter of the world. The torch of celestial knowledge was not extinguished with the fading of the classical world. It was carried forward into a brilliant new era of scholarship that blossomed under the caliphates. In the vibrant intellectual capitals of Baghdad and Damascus, a monumental project was underway, one fueled by a deep curiosity about the universe. Caliphs and wealthy patrons sponsored massive translation movements, gathering teams of scholars to render the great works of the Greeks, Persians, and Indians into Arabic. The legendary Greek texts like Ptolemy's Almagest, which itself was built on Babylonian data, were now meticulously translated, studied, and critically examined. This was not a simple act of preservation, it was a rebirth. At the heart of this renaissance was the House of Wisdom in Baghdad, an institution that functioned as a university, library, and translation center all in one. Here, in buzzing scriptoriums, manuscripts were not just copied, they were corrected, debated, and expanded upon by a community of the finest minds. The ancient Babylonian numbers and Greek geometry were now being processed through a new, dynamic intellectual filter. Brilliant astronomers like Al-Batani took the old data and made it better. He spent decades making his own observations, refining the parameters for planetary motion, and producing astronomical tables of stunning accuracy that would be used for centuries. Then there was Al-Khwarizmi, a scholar whose name would give us the word algorithm. In his pursuit of solving astronomical and inheritance problems, he systematized a new form of mathematics, which he called al-Jabr or algebra. This was a revolutionary step, a move from the geometry of the Greeks to a more abstract and powerful language of equations, a language that would one day be essential for describing the force of gravity. The most tangible products of this golden age were the etched, comprehensive astronomical handbooks that combined theory with practical tables. These etched wove together the entire thread of celestial knowledge, from ancient Babylonian eclipse cycles to Greek models and the latest Islamic observations. They were the working manuals for astronomers, navigators, and timekeepers, ensuring the data was not just preserved in a library, but actively used and tested. The manuscript trail, now written in the elegant script of Arabic, was not only safe, it was richer and more precise than ever before. But empires rise and fall, and the political stability that nourished this golden age would not last forever. The question now became, which door would this enhanced knowledge use to finally make its way into Europe? The door to Europe was not a grand palace gate, but a quiet scriptorium in a city where cultures collided. Toledo, Spain, after its reconquest by Christian forces, became a living library of Arabic knowledge. Here, a scholar from Italy named Gerard of Cremona arrived in the 12th century, driven by a singular obsession. He had heard of Ptolemy's Almagest, a legendary text of Greek astronomy that had been lost to the Latin-speaking West for centuries, but which was preserved and perfected in Arabic libraries. Gerard found himself in a world where the air was thick with the sounds of three languages, where Christian, Jewish, and Muslim scholars worked side by side. His mission was monumental: to learn Arabic and translate this vast cosmic encyclopedia, along with dozens of other scientific works, into Latin. This was not a simple word-for-word swap. It was an act of intellectual archaeology, digging through layers of commentary and refinement added by generations of Islamic astronomers to recover the original Greek framework, now supercharged with new data and insights. Gerard and his team of translators labored for years, their quills scratching across parchment, carefully turning phrases about planetary equations and celestial spheres from one complex language into another. They were not just translators, they were conduits. In their work, the Babylonian planetary data, which had been filtered through Greek geometry and then enhanced by Islamic mathematics, finally entered the mainstream of European thought. The painstaking work of these scribes created a bridge across a chasm of centuries and cultures. Suddenly, the universities of Paris, Oxford, and Bologna had access to this river of knowledge. Lecturers could now stand before eager students and present a complete model of the cosmos, a system with predictive power that was rooted in observations dating back to ancient Mesopotamia. This influx of translated manuscripts ignited a firestorm of intellectual curiosity. For the first time in centuries, European thinkers could engage with a sophisticated, mathematical astronomy. They could see the heavens not as a realm of pure mystery, but as a clockwork of incredible complexity, one that could be measured, analyzed, and understood. The stage was now set, but the old models were about to face their greatest challenge. Could this ancient cosmic clockwork, perfected over millennia, withstand the scrutiny of a new age of observation? Inside the cold stone halls of Oxford and Paris, a new kind of mind was being forged. These medieval universities taught astronomy not as a separate science, but as one of the four mathematical arts, the quadrivium, a curriculum that sat alongside arithmetic, geometry, and music. This was a profound connection, linking the motion of the planets directly to the harmony of numbers and the logic of shapes. A student training in this system did not just memorize star charts, they learned to see the universe itself as a complex mathematical composition. The very texts they pored over, the translations from Gerard of Cremona and others, were living fossils within the Latin diagrams of celestial spheres and the tables predicting a planet's position. lay the ghostly fingerprints of Babylonian observers, data that had traveled from clay to papyrus to parchment. This institutional framework was the crucible. It took this ancient hybrid knowledge and made it the common property of a rising intellectual class. For the first time, a scholar in England and a thinker in Italy were working from the same cosmic playbook, debating the same geometrical models, and wrestling with the same numerical inconsistencies they found in the old tables. The university did not just preserve this knowledge, it made it a subject of critical debate. It created a community, a network of brilliant, restless minds who were taught to respect the ancients, but not to worship them blindly. They were handed a complete system of the world, a gift wrapped in the authority of Ptolemy and Al-Batani, and their first instinct was to look for the cracks. This shared foundation, this common language of the cosmos, was the essential training ground. It produced the very thinkers who would one day have the audacity to dismantle the very models they had so carefully studied. How could a system so complete, so deeply embedded in the curriculum, ever be overturned? The answer was already taking shape, not in the lecture hall, but in the observatory. A king's obsession with the stars would cement the legacy of Babylonian mathematics for 3 more centuries. In the royal court of 13th century Castile, King Alfonso X, a monarch known as the Wise, gathered the finest minds from the 3 great faiths of his kingdom. Jewish, Christian, and Muslim scholars sat together, their task not driven by conquest but by calculation. They pored over the accumulated wisdom, the Arabic Zijs, the Greek models, all of it built upon that ancient Mesopotamian foundation. Their goal was not just to copy, but to correct, to create the most accurate set of predictive astronomical tables the world had yet seen. The result was the Alphonsine tables, a computational marvel that would become the gold standard for European astronomy. Imagine the sheer labor involved, the endless checking of numbers, the debates over a fraction of a degree in a planet's path. These were not just star charts, they were a complex engine of prediction, calculating the future positions of the sun, moon, and planets with a precision that felt almost like magic. And at the very core of this engine, running like a steady, ancient heartbeat, were the numerical methods first devised by Babylonian scribes. Their base 60 system, their parameters for lunar motion, their very approach to modeling the sky were all refined and embedded within these new tables. When the Alphonsine tables spread from Spain to the universities of Europe, they carried this hidden lineage with them. For the next 300 years, any student in Paris, any astronomer in Prague, any navigator plotting a course would have consulted these tables. They were the practical tool that turned cosmic theory into actionable data, used to cast horoscopes, determine the dates of religious festivals, and guide ships across unknown seas. This was not a dusty relic, it was living knowledge, and its authority was absolute. Yet, the very success of these tables created a paradox. The more astronomers used them, the more they began to notice tiny, persistent errors. The clockwork universe perfected in Castile was starting to show its age. How long could a system built on ancient numbers continue to hold back the tide of new observations? A new kind of machine began to whisper the language of the stars across Europe. The invention of movable type in the 15th century did not just make books easier to produce, it fundamentally transformed the very nature of knowledge itself. Before the printing press, a manuscript was a unique, fragile artifact, copied by hand with all the inevitable slips of the pen and personal interpretations of a tired scribe. Now, for the first time, a complex astronomical table or a detailed geometrical diagram could be reproduced not just once, but hundreds of times with perfect mechanical fidelity. The Alphonsine tables, that crown jewel of Castilian astronomy built on Babylonian numbers, were among the very first scientific works to be printed. Suddenly, An astronomer in Krakow and a navigator in Lisbon could be looking at the exact same numbers, calculated from the same ancient parameters. This was a revolution in accuracy. The long data chain, which had passed from clay to papyrus to parchment, was now being stamped indelibly onto paper, its integrity locked in. Standardization meant that scholars could now debate from a common, unchangeable text, building upon a solid foundation rather than wasting years trying to correct a corrupted copy. But the press did more than just preserve, it also annotated and explained. Printed editions often came bundled with extensive commentaries. In the margins of these new books, you might find a scholar tracing a particular computational method or a planetary parameter all the way back to its origins, sometimes explicitly noting its debt to the Chaldeans, the ancient term for the Babylonians. The hidden lineage was now being printed in plain sight for anyone who knew how to read the clues. This mass dissemination created a critical mass of informed thinkers. It was no longer a secret held by a few elite institutions, but a living, breathing field of study debated in cafes and correspondence across the continent. The old knowledge, now perfectly preserved and widely available, ironically created the conditions for its own overthrow. How could a single observer with a new idea hope to challenge a system that was now printed, bound, and distributed to every major center of learning? The answer was that the press gave that observer a megaphone. Nicolaus Copernicus sat surrounded by a fortress of manuscripts, the very air thick with the weight of ancient authority. He was not a rebel setting out to destroy the past, but a scholar trying to solve a puzzle that had troubled astronomers for centuries. The planetary motions predicted by the Alphonsine tables, for all their precision, were beginning to drift from what could be seen in the night sky. The old cosmic clockwork was grinding, its gears worn by 1,000 years of tiny, accumulated errors. His solution was breathtakingly radical: to place the sun, not the earth, at the center of the universe. Yet the evidence he used to build this new model was profoundly ancient. In his hands were the very texts we have been following, the Latin translations of Greek and Islamic works, all of them saturated with data whose origins lay in Babylonian clay. He pored over eclipse records and planetary cycles that Islamic astronomers like al-Battani had refined, data that could be traced back to the meticulous observers of Nineveh and Babylon. This was not a rejection of history, but its fulfillment. His great work, De Revolutionibus, openly acknowledges this immense debt, standing on the shoulders of giants who themselves stood on the shoulders of Mesopotamian scribes. The revolutionary heliocentric model, which would shatter a worldview that had stood for millennia, was built using the oldest observational tools humanity possessed. The numbers first used to advise Assyrian kings were now being used to dethrone the earth itself. How could a system so deeply embedded in tradition become the very instrument of its own destruction? The answer lies in the relentless honesty of the data itself, a truth that patiently waited centuries for a mind prepared to listen. On a small island in the Sound between Denmark and Sweden, a castle of science named Uraniborg pierced the sky. This was the creation of Tycho Brahe, a man with a singular obsession: to measure the heavens with a precision the world had never seen. Within his observatory, giant brass quadrants and sextants, some as tall as a person, were fixed in place, their finely engraved arcs allowing Tycho and his team to track planetary positions to an accuracy of a single minute of arc, a sliver of a degree. This was not casual stargazing, it was a systematic, industrial-scale project of data collection, a direct and conscious echo of the Babylonian tradition of long-term celestial diaries. For over 20 years, night after night, his team recorded the movements of the planets, especially the wayward path of Mars, generating a mountain of empirical evidence. This new gold standard of data immediately exposed the flaws in the old systems. The Alphonsine tables, for all their ancient authority, were now demonstrably wrong, sometimes by a full degree or more. Tycho's instruments had become so precise that they could hear the subtle cracks in the crystal spheres of the old cosmology. His work was the culmination of an ancient legacy, the final, most accurate link in a chain of observation that began with clay and stylus. Yet Tycho himself was a man caught between worlds, crafting his own complex model of the solar system that still kept the Earth at its center. He had gathered the most valuable treasure an astronomer could possess, a perfect map of the sky, but he lacked the key to unlock its deepest secret. That key would be forged by the brilliant, troubled mind of his assistant, a man who saw in this data not just points on a chart, but the hidden music of the universe. Johannes Kepler inherited a mountain of numbers, the legacy of Tycho's relentless observations. For years, he wrestled with the orbit of Mars, a puzzle that refused to be solved by the perfect circles demanded by ancient Greek philosophy. He trusted the data, the hard numbers passed down through generations, more than he trusted the elegant geometric models. This was a man who believed the universe was built on a hidden mathematical harmony, a divine geometry. But he was also a scientist who knew that if his beautiful theory did not match the ugly, stubborn facts, then the theory had to be wrong. He tried dozens of circular paths, each one failing to predict the planet's position as recorded in Tycho's priceless logs. The breakthrough came when he abandoned 2,000 years of assumption. The orbit was not a circle, it was an ellipse. With this single revolutionary insight, the cosmos snapped into a new and breathtaking focus. He had discovered his first law of planetary motion. But he did not stop there. He went further, realizing that a planet does not sweep out equal areas in equal times because it wants to, but because something physical was making it do so. A planet speeds up as it gets closer to the sun and slows down as it moves away, tracing equal areas in its elliptical path. This was no longer just a description of motion, it was a clue to its cause. Kepler was now peering into the machinery of the heavens, suggesting an invisible force emanating from the sun itself. His three laws were a direct product of that long manuscript trail. The Babylonian obsession with prediction, the Greek love of form, the Islamic refinement of parameters, all culminated in this moment. Kepler had used the world's oldest data to reveal one of nature's most fundamental truths. He built a conceptual bridge from the ancient stargazers to a new physics, a bridge strong enough to carry the weight of a genius yet to come. Who would be the one to cross that bridge and finally ask what force could bend the paths of the planets into such elegant ellipses? These private libraries became the quiet engines of the scientific revolution. In the 17th century, the most powerful tool for an intellectual was not a telescope, but a library card. Men like John Dee in England amassed personal collections of staggering breadth. Rooms filled floor to ceiling with leather-bound manuscripts and newly printed books. These were not just random accumulations, but carefully curated archives of the world's knowledge. Within these hushed, paper-scented spaces, a scholar could pull down a Greek copy of Ptolemy's Almagest, place it beside a Latin translation of an Arabic Zij, and open a printed edition of Copernicus, all on the same desk. For the first time, the entire 3,000-year chain of celestial thought was laid out side by side, a living timeline of discovery. The real magic happened in the cross-referencing. An astronomer could trace a single number, like the precise length of the solar year, from a modern table back through its Arabic refinement to its Greek adoption, and see its origin in a Babylonian clay tablet's cuneiform notation. This was historical detective work on a grand scale. It allowed thinkers to see astronomy not as a set of fixed truths, but as an evolving conversation. They could identify which parts of the old models were robust, having survived centuries of testing, and which parts were fragile, added by later commentators and now ripe for challenge. This access to primary sources was absolutely essential. It provided the raw, unvarnished data from which new syntheses could be built. A scholar was no longer forced to rely on a single, potentially flawed textbook. He could go directly to the source, to the original observations and calculations, and judge for himself. These collections, both private and institutional, functioned as a kind of intellectual seed bank, preserving every strand of the celestial data chain. They ensured that the next great mind, a mind like Isaac Newton, would not have to start from scratch. He would instead walk into a library and find the entire history of astronomy waiting for him, a puzzle that had been patiently assembled over millennia, with one final, crucial piece still missing. What kind of mind could look at this sprawling, chaotic history and see within it a single, unifying law? While Newton worked in solitude, the world of science was buzzing with conversation. A quiet revolution was taking place not in observatories but in the post. A web of letters carried by horse and ship connected thinkers from London to Paris, from Italy to the Netherlands. At the center of this network were men like Marin Mersenne in Paris and Henry Oldenburg in London, who acted as human switchboards for the entire Republic of Letters. Their desks were not just places of study, but clearinghouses for the latest discoveries. A letter arriving from Denmark might contain a new observation of a comet, while a packet from Poland could hold a fierce critique of Kepler's ellipses. These were not private notes, they were public documents in miniature, meant to be read aloud, copied, and debated. This correspondence network became the nervous system of European science, pulsing with data and theory. It ensured that a breakthrough in a small German town did not die in isolation, but could spark an idea in the mind of a Cambridge professor within weeks. The very topics we have been tracing, the ancient Babylonian parameters and the refined data from Islamic astronomers, were constant subjects in this transcontinental dialogue. Scholars would write to each other questioning the accuracy of an old eclipse record mentioned in a Greek text, or sharing a newly translated passage from an Arabic manuscript that offered a different computational method. These letters kept the ancient manuscript trail not as a dusty relic, but as a living, breathing part of current research. The collaborative spirit was electric and profoundly practical. It accelerated the process of science by orders of magnitude, creating a fertile, shared intellectual space where the past was constantly being sifted and integrated into the present. This was the environment that would nurture Newton's genius, a world already prepped with every piece of the puzzle, waiting for the one mind that could see how they all locked together. The dusty plains of Mesopotamia yielded a secret in the 19th century, a truth that had traveled the world only to be rediscovered at its source. Archaeologists like Henry Rawlinson stood before the great cliff face of Behistun in Persia, carefully copying down the strange, wedge-shaped symbols that had been silent for 2,000 years. This was cuneiform, the ancient script of Mesopotamia, and its decipherment was a key turning a lock no one knew still existed. When the language finally gave up its secrets, the modern world was granted a stunning privilege, a direct window into the original observatories of Babylon. Scholars could now read the astronomical diaries for themselves, clay tablets that recorded the night sky on a specific date, like the 26th of Adaru in the 37th year of King Nebuchadnezzar. They found meticulous observations of Jupiter's first appearance, of lunar eclipses, and of planetary conjunctions, all noted with a matter-of-fact precision. Even more astonishing were the mathematical tablets, which laid out the step-by-step procedures Babylonian astronomers used to predict celestial events. Here was the actual algorithm, the computational engine that powered their predictions. This was not a myth or a legend passed down through distorted copies. This was the raw data, the original source code for the cosmos as they understood it. The long chain of transmission from Greek to Arabic to Latin was suddenly and powerfully validated. Every parameter, every number that had been so carefully preserved and handed down by generations of scholars was now proven to be authentic. The ghostly fingerprints that had been faintly visible in the works of Ptolemy, Albertoni, and Kepler were now confirmed as the very real marks of a stylus on clay. This archaeological recovery added a profound new layer of authenticity to our story. It proved that the manuscript trail was not based on whispers or lucky guesses, but on a solid foundation of empirical science. The data that helped Newton see the universal law of gravitation was not just old, it was impeccably recorded, calculated, and real. How does this final, physical proof reshape our understanding of science's greatest leap? A young Isaac Newton was not the isolated genius of legend, but a scholar drowning in books. In his Cambridge rooms, surrounded by a fortress of leather-bound volumes, he was on a quest. He believed the ancients held a secret, a pristine wisdom they called Prisca Sapientia, a perfect understanding of nature that had been lost to the modern world. His notebooks from this period are a labyrinth of ideas, filled with frantic studies of Pythagoras and the mystical Hermetic texts, all in search of this hidden key. He was convinced that figures like Pythagoras had access to a cosmic truth, a knowledge of universal harmonies that later ages had corrupted or forgotten. This was not a mere historical curiosity for Newton, it was the very engine of his research. He saw himself not as an inventor of new ideas, but as a restorer of ancient ones, a detective piecing together a puzzle that had been scattered by time. This profound belief in the continuity of knowledge drove him directly to the sources we have been following. He pored over the available Latin translations of medieval astronomers, men who had themselves worked with the data from the Islamic Golden Age, which in turn was built upon Greek and Babylonian foundations. He saw in the precise numerical observations of the Babylonians something extraordinary. Their long-term records of the heavens were not just data, they were fragments of that lost Prisca Sapientia, a direct line to a time when humanity understood the mathematical language of God's creation. This conviction that ancient wisdom and modern mathematics were two sides of the same coin set the stage for everything that would follow. His monumental work, the Principia Mathematica, would become the ultimate synthesis, a fusion of ancient observation and a new, powerful calculus. But what specific ancient problem, a flaw in the old cosmic clockwork, would finally force that synthesis into being? The moon was falling. That was the thought that struck Isaac Newton, not as a poetic fancy, but as a physical reality. If the moon orbits the Earth, what keeps it from flying off into the void? His mind connected the arc of a thrown apple to the curved path of our celestial companion. Both were falling, one toward the ground, the other perpetually toward the Earth, its fall perfectly balanced by its forward motion. To prove this audacious idea, he needed two things: a new kind of mathematics to describe continuous change, and the most accurate data on planetary motion the world could offer. He forged the mathematics himself, inventing the calculus, a tool for tracking the flow of the universe. For the data, he turned to the work of Johannes Kepler. Kepler's three laws were the final, crucial piece of the puzzle. His first law stated that planets move in ellipses, not circles. His second law revealed that a planet speeds up as it nears the sun. And his third law provided a precise mathematical relationship between a planet's orbital period and its distance from the sun. These were not just descriptions, they were clues written in the language of geometry and numbers. Newton took these laws and, with the power of his new calculus, performed a feat of mathematical synthesis. He demonstrated that all three of Kepler's laws could be derived from a single, universal principle, that every particle of matter attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This was the law of universal gravitation. It was the grand unification. The same force that pulled an apple to the ground held the moon in its orbit, guided the planets around the sun, and dictated the tides. Celestial mechanics and earthly physics were not separate realms. They were one and the same, governed by a single, elegant equation. Yet this revolutionary leap rested on a foundation far older than Kepler. The planetary data that Kepler had wrestled with, the precise positions of Mars that refused to fit into circular orbits, were the legacy of Tycho Brahe's observatory. And Tycho's lifelong project was a direct, conscious continuation of an ancient tradition, the same tradition of meticulous, long-term observation that began with the Babylonian stargazers. The numbers that allowed Newton to verify his theory, to check his calculations against the actual behavior of the cosmos, were the same numbers first calculated on clay tablets to advise Mesopotamian kings. His monumental work, the Philosophiae Naturalis Principia Mathematica, did not emerge from a vacuum. It was the culmination of a 3,000-year-long conversation, a conversation that began with empirical records etched in damp clay. Newton showed the world that the universe operates by consistent mathematical laws, but he also demonstrated something equally profound about the nature of knowledge itself. That ancient data, patiently preserved and refined across cultures and centuries, holds the power to unlock truths that its original collectors could never have dreamed of. The manuscript trail did not just preserve an idea, it built a ladder, and Newton was the one who climbed it to touch the stars. Newton was not content to simply use the data, he wanted to converse with its original authors. In his private study, surrounded by a chaos of books and papers, he embarked on a monumental project of historical reconstruction. He pored over every ancient source he could find, from Greek myths to the faint, translated accounts of Babylonian kings, attempting to synchronize their celestial records with the timeline of biblical history. For Newton, this was not a separate hobby from his physics. It was the same investigation pursued through a different lens. He was convinced that the earliest astronomers, the wise men of Babylon and Egypt, possessed a profound understanding of the cosmos, a knowledge he called the Prisca Sapientia, which had been lost or corrupted over time. He believed they had known about the force of gravity, not as a mathematical equation, but as a philosophical principle governing the harmony of the spheres. His voluminous writings on chronology are filled with attempts to prove this, to find hints of universal gravitation hidden within ancient fables and king lists. He saw the incredible stability of certain astronomical cycles, parameters for the moon and planets that had remained consistent from Babylonian times to his own, as powerful evidence. Why would these numbers persist for millennia unless they were tapping into a fundamental, unchanging truth about the universe? His correspondence with other scholars reveals a man obsessed with validating his theory against the oldest possible observations, treating an eclipse record from the reign of a Babylonian king as a crucial data point that could confirm or challenge his laws. This was the manuscript trail at its most dynamic. It was no longer a one-way street of data flowing from the past to the present. Newton was actively talking back, interrogating the ancient sources, asking them questions they were never designed to answer. He was using his new physics to decode their world, and using their ancient world to vindicate his new physics. This dialogue across 3,000 years enriched his science, grounding his most abstract concepts in the deep, solid bedrock of historical observation. If the cosmos was a book written in the language of mathematics, then the oldest chapters held the key to understanding the plot. What does this tell us about the very nature of scientific discovery? It suggests that the greatest leaps forward are not always a break from the past, but sometimes a deeper, more thoughtful listening to its oldest whispers. That ancient base 60 system, born from Babylonian stargazers, became the silent engine of celestial calculation for 3,000 years. It was more than just a number system. It was a robust computational language perfectly suited for the heavens, a language of fractions and angles that refused to become obsolete. When the Greeks adopted it, they saw its elegance for dividing the circle into 360 degrees, a number divisible by so many factors it made complex geometry manageable. This was not a mere historical curiosity. It was the practical toolkit that allowed Ptolemy to build his complex model of epicycles and equants, calculating planetary positions with a precision that would stand for centuries. The system's resilience is astonishing. You can trace its unbroken use from clay tablets in Nineveh to the observatories of medieval Islam, where scholars like al-Battani used it to refine the length of the solar year, and then into the Latin manuscripts of European universities. It was the standard for navigation at sea, for mapping the stars, for setting the calendar. This was the intellectual infrastructure, the shared software upon which every astronomer relied. When Johannes Kepler wrestled with Tycho Brahe's data on the orbit of Mars, he was working within this very framework, using sexagesimal arithmetic to pinpoint the planet's position to a fraction of a degree. His discovery of elliptical orbits depended entirely on the precision these ancient methods afforded. And so, when Isaac Newton sat down to write his Principia, this computational tradition was the water in which he swam. The mathematics he used to demonstrate universal gravitation, the calculus of fluxions he invented to track continuous motion, all rested upon a numerical foundation laid millennia earlier. The Babylonian preference for base 60 facilitated the delicate fractional calculations needed to compare the falling moon to a falling apple, to balance the forces of attraction and inertia. Newton did not just inherit raw data from the past, he inherited a fully functional and time-tested way of processing that data. The methods for predicting an eclipse, first codified on clay, had been refined and transmitted through countless hands, ensuring that the intellectual tools needed to unlock the cosmos were sitting ready on his desk. How many other invisible architectures of thought perfected by forgotten minds are we still using today without ever knowing their origin? Newton's world was electrified by a powerful new idea, the belief that progress lay in recovering a lost golden age. The Renaissance had unlocked a treasure chest of ancient texts, and scholars across Europe were not just reading them, they were trying to rebuild a forgotten world of wisdom. This was not simple nostalgia, it was a forward-looking philosophy, a conviction that the path to the future was buried in the past. The manuscript trail we have been following was not seen as a curiosity, it was a source of immense authority. When a scholar like Newton read a Latin translation of an Arabic astronomical table, he was not looking at a dead document, he was holding a piece of a grand puzzle. This intellectual climate encouraged a profound respect for verification. If an ancient text claimed the Babylonians could predict eclipses, a 17th century thinker felt compelled to check that claim against the sky to see if the old knowledge still held true. This process of testing and rediscovery forged a direct link between past and present, transforming historical records into active participants in contemporary science. The sheer sophistication of Babylonian astronomy, now becoming clearer through these recovered texts, delivered a seismic shock to the European worldview. It shattered the comfortable assumption that all meaningful science began with the Greeks. Here was undeniable evidence of a highly advanced, non-Western civilization that had mastered the mathematics of the heavens millennia before. This forced a radical and humbling realization that scientific genius was not the sole property of one culture or continent. It was a universal human endeavor. This shift was crucial. It created a cultural receptiveness to the idea that science is a collaborative project spanning centuries. Newton did not see himself as a lone genius inventing physics from nothing. He saw himself as a link in a very long chain, standing on the shoulders of the giants who came before him, from the Greeks and the Islamic scholars all the way back to the anonymous scribes of Mesopotamia. His monumental work was, in his own mind, a restoration of a pristine truth that the ancients had already glimpsed. The very act of looking backward, of valuing that ancient manuscript trail, is what ultimately propelled science forward into a new age. What other long-forgotten conversations are we still missing, simply because we have not yet learned how to listen? These great libraries were the silent partners in every scientific revolution. Within the hallowed halls of Oxford's Bodleian Library, the collections at Cambridge, and the nascent Royal Society in London, the entire manuscript trail we have traced was physically gathered under one roof. This was not a scattered legacy, but a concentrated archive. A scholar like Newton could request a Greek manuscript of Ptolemy, place it beside a Latin translation of an Arabic Zij, and open a freshly printed copy of Kepler's Rudolphine tables, all on the same heavy wooden desk. For the first time, the entire 3,000-year conversation, from Babylonian clay to European paper, could be laid out side by side for direct comparative study. This convergence was everything. It allowed for a new kind of historical verification, where a number in Kepler's work could be cross-checked against its appearance in a medieval Latin text, and then traced further back to its origin in an Arabic commentary, creating an unbroken chain of evidence. The true architects of this knowledge network were often the unsung librarians and curators, the men who catalogued, repaired, and organized these precious texts. They fought the slow decay of parchment and ink, rebinding volumes and painstakingly copying fragile manuscripts to ensure their survival. Their meticulous work created a reliable, searchable repository, turning a chaotic pile of books into a functional tool for discovery. Without these organized archives, the chain of knowledge would have remained a series of isolated links. The librarian who carefully shelved a new acquisition next to an ancient text was physically building the bridge between eras. These institutions guaranteed that no single discovery needed to be made twice, that every old observation remained available to challenge or confirm every new theory. They provided the stable, documentary bedrock upon which the soaring cathedral of modern science could be built. What other revolutions are waiting in the quiet aisles of a library, simply for the right mind to connect the dots? The true test of any data is its power to predict the future. As early modern astronomers pointed their new telescopes skyward, they held in their hands the ancient records passed down through the ages. They began a grand experiment, checking the celestial events recorded by Babylonian scribes against what they could now see with their own enhanced eyes. The results were startling. Timings of lunar eclipses calculated on clay tablets millennia ago aligned almost perfectly with the events unfolding in their telescopic eyepieces. The long-term planetary cycles, those intricate dances of Jupiter and Saturn noted in cuneiform diaries, were confirmed by centuries of subsequent observation. This was not a vague philosophical agreement, it was a precise numerical validation. The ancient numbers were not just historically interesting, they were scientifically sound. This process of verification transformed the manuscript trail from a curious historical artifact into a trusted scientific instrument. It proved that the chain of transmission, for all its twists and turns through different languages and cultures, had preserved something incredibly precious, the raw, empirical truth of the sky itself. A brilliant demonstration of this power came from Edmund Halley. He delved into historical records, sifting through accounts that could be traced back to ancient Babylonian sources, looking for patterns in the appearance of comets. By trusting this long chronological data, he noticed that the comet he observed in 1682 had orbital elements strikingly similar to comets reported in 1531 and 1607. He made a breathtaking prediction, stating that this was the same comet returning on a 76-year cycle and that it would reappear around 1758. When it did, just as he foretold, it was a triumph not only for Newtonian physics but for the entire historical enterprise of astronomy. Halley's comet, as it became known, was a direct result of trusting the ancient manuscript trail. This iterative checking, this constant conversation between past observation and present verification, solidified a profound truth. The data carried across 3,000 years was not merely preserved, it was alive, continually proving its worth against the relentless scrutiny of time and technology. The numbers etched in clay were not whispers from a dead past, but a durable thread connecting human curiosity across the ages. The same manuscript trail that guided Newton to gravity also illuminated his path through the nature of light itself. While his laws of motion often claim the spotlight, his revolutionary work in optics was equally built upon a foundation of ancient and medieval inquiry. In his quiet Cambridge rooms, he would have encountered the writings of Islamic scholars like Alhazen, whose own groundbreaking book of optics systematically explained how vision worked, not through rays emanating from the eye as the Greeks had thought, but through light traveling in straight lines into it. Alhazen's work was itself a synthesis, drawing from Greek sources and potentially even earlier traditions, creating a 1,000-year-old conversation about the very essence of sight and color that landed on Newton's desk. This was not a solitary genius working in a vacuum, but a scholar engaging with a continuous line of questioning. When Newton began his famous experiments with a prism, splitting a beam of sunlight into a vibrant spectrum, he was entering a debate that had been alive for centuries. He was testing and refining ideas that had been passed down, challenged, and improved by generations of thinkers before him. His resulting theory, that white light is actually a mixture of all colors, and that color is a fundamental property of light itself, was a decisive answer to a very old question. This parallel trail in optics reveals a crucial truth about the flow of knowledge. It was not a single river leading only to astronomy, but a vast, interconnected delta feeding multiple scientific disciplines simultaneously. Newton's own mind was a place where these streams converged. His holistic approach meant that the mathematical rigor he applied to planetary orbits could also inform his understanding of light waves, and the empirical methods he learned from ancient astronomical records guided his hands in a darkened room with a prism. The preserved wisdom on optics provided him with the foundational concepts, the failed theories, and the accumulated data that allowed him to see further. It gave him the questions so he could dedicate his genius to finding the answers. How many other scientific revolutions began not with a new idea, but with an old manuscript patiently waiting for its moment to shine? Newton's laws did not descend from the void fully formed. They were the final, elegant expression of a conversation that began when the first Babylonian astronomer noticed a planet returning to the same patch of sky. That core concept, the very predictability of the cosmos, is the bedrock of Newtonian physics. His first law, the principle of inertia, states that an object at rest stays at rest, and an object in motion stays in motion unless acted upon by a force. But to even conceive of such a law, Newton first had to believe the universe was governed by consistent, repeatable rules. Where did that belief come from? It came from the data. For centuries, the manuscript trail had delivered the same unshakable message. The planets do not wander randomly, they follow patterns. The moon's eclipse does not happen by whim. It recurs in cycles so reliable they can be calculated centuries in advance. This was the great, unspoken premise that the Babylonians gifted to the world, a cosmos that could be trusted to behave. Without that foundational faith in cosmic order, Newton's search for universal laws would have seemed like a fool's errand. His law of universal gravitation was the ultimate payoff for that faith. The same mathematical relationship that explained why an apple falls also explained the precise, elliptical orbit of Mars, an orbit whose parameters were refined by Kepler using data from Tycho Brahe, who was consciously emulating the long-term observational projects of the Mesopotamians. Every link in that chain was essential. The revolutionary power of Newton's system was that it validated the entire sprawling manuscript trail. It proved that the patient, cumulative work of generations was not merely preservation, but a form of collective problem-solving on a scale no single lifetime could achieve. The Babylonian scribe who recorded the position of Jupiter was not just serving his king, he was, without knowing it, placing a single day to point into a calculation that would one day help define a force that binds the universe. This is the true nature of scientific revolutions. They are not sudden explosions that erase the past, but magnificent syntheses that make sense of it. They are the moment when scattered whispers from across the ages finally coalesce into a clear, undeniable voice. So the next time you hear of a lone genius having a eureka moment, look closer. You will almost always find them standing on a pyramid of parchment and clay, built by thousands of forgotten hands. What other pyramids of knowledge are we building right now whose ultimate purpose we cannot yet see? Modern technology is giving us a magnifying glass to examine this ancient chain of knowledge. Historians of science are now using computational analysis and digital humanities to read the old texts in ways their original authors could never have imagined. Entire libraries of clay tablets and medieval manuscripts are being meticulously scanned and digitized, creating a vast, searchable database of the celestial past. This is not just about preservation, it is about connection. For the first time, a scholar can run an algorithm to compare a planetary parameter from a Babylonian tablet with its appearance in a Greek papyrus, an Arabic zij, and a Latin commentary, all within minutes. They can trace the life of a single number as it traveled across continents and centuries, watching how it was subtly adjusted, corrected, or reinterpreted by each new generation of astronomers. This granular analysis confirms the grand narrative of transmission, but it also reveals something more intimate, the intellectual fingerprints of individual scribes and scholars. We can now see where a medieval translator might have struggled with a tricky Arabic phrase, introducing a tiny error that would echo for 100 years. We can identify when a Greek astronomer like Ptolemy made a conscious choice to smooth out raw Babylonian data to fit his elegant geometrical models. These are not mistakes, they are conversations. Each adjustment tells a story about how different cultures, with their own philosophical priorities, engaged with the same set of cosmic facts. This deep dive enriches our appreciation for every link in the chain. It shows us the Babylonian not just as a data collector, but as a sophisticated mathematician developing abstract functions. It reveals the Islamic astronomer not as a mere preserver, but as a critical innovator who tested and refined the old numbers against his own rigorous observations. The modern reassessment does not diminish the story, it adds breathtaking detail, proving that the path to Newton was paved with countless individual acts of genius, scrutiny, and care. What other hidden dialogues are waiting to be heard in the silent script of these digitized pages? From the clay tablets of Mesopotamia to the desk of Isaac Newton, this 3,000-year journey reveals a truth more profound than any single discovery. The real miracle was not Newton's genius alone, but the survival of the very data that made it possible. This manuscript trail is a testament to a fundamental reality, that science is a relay race through time, not a series of solo sprints. It asks us to redefine what we mean by a scientific revolution. These are not explosions that obliterate the past, but moments of synthesis where scattered pieces of an ancient puzzle finally click into place. The Babylonian scribe, the Alexandrian librarian, the Baghdad translator, the Oxford professor, they were all partners in the same grand investigation. Their collective work ensured that a calculation made for an Assyrian king could one day help a mind in England decipher the universal force of gravity. This story challenges the myth of the isolated genius working in a vacuum. Every great leap forward stands upon a pyramid of parchment and clay, built by thousands of forgotten hands. So the next time you look up at the moon, remember that its orbit was mapped not just by Newton, but by the cumulative curiosity of our entire species. What other conversations started long ago are we still a part of today without even realizing it? We would love to hear which part of this incredible journey surprised you the most. Share your thoughts below, and if you enjoyed tracing this hidden connection, subscribe for more explorations into the stories that bind our world together.